I'm here with Ivan Tashev, Principal Software Architect at Microsoft Research. He's known as the brains, or at least the ears, at Microsoft. And you're behind the acoustic breakthroughs in the original Kinect, as well as the Kinect on Xbox One, and other products like Roundtable, Microsoft Automotive, and you worked on the microphone array support that started with Vista.
That's correct.
Yeah, you've shipped a lot of products for a researcher.
I have been here for a long time.
How long have you been at Microsoft?
15 years.
And so you originally came from Bulgaria?
That's correct.
And what was the path that led you here to Microsoft?
At that time, I was assistant professor in the Technical University of Sofia, my alma mater. Actually, I have worked for two companies only, Technical University of Sofia and Microsoft. And at some point, was tempted to switch from academia to industry and to see, okay, it's good to teach students and good to make a nice and cool theoretical work. Can this thing work in reality? Can we make some of the algorithms which are easy to derive on paper to be part of an industrial device, to make the transition from algorithms for microphone arrays to algorithms for manufacturable microphone arrays in quantities?
So explain what the difference is between a microphone array and a regular microphone.
So a regular microphone is one point in the space where we pick the sound. A microphone array contains at least two, in the Kinect case, 4 microphones like this, and those 4 microphones give us the sense of direction. So we can combine the signals from the 4 channels in a way to make the microphone array to listen towards given direction and to suppress the sounds coming from other directions, which means that at the end the resulting effect is that we get one channel of a better microphone, highly directional, but we can electronically steer the direction we can listen to. We can electronically place a null towards a competing sound source. We can electronically steer this null. So as a result, we adaptively are getting the best possible sound from the desired direction, minimizing the noise coming from other directions.
And so you can tell where in space a sound is coming from. How accurate is that?
So this technology is called sound source localization. We have it in Kinect and in Xbox One because we have to know where to point the beam. And the precision is 3-4 degrees, which is sufficiently to pinpoint the beam inside the mouth at 4 meters distance.
And how does a human work so well with just 2 microphones? Is it a lot of CPU?
First, we have 2 microphones, which is important. So it's a microphone array, it's not a single point. Yeah. And second, we have a substantial amount of CPU power between the 2 microphones. It's 100 billion neurons, yeah. A computing power we will not have for audio processing in foreseeable future.
Yeah, it'll be a little while. And what are some of the hardest noises to remove?
So in Kinect, we have 2 major enemies, 2 major noises we have to remove. Noises we know about, that's the sound from the loudspeakers. Mm-hmm. And noises we don't know about. This is the room noise, the noises from the street, from across the street, etc., etc. And happening that the noises from the loudspeaker are most difficult to remove by 2 reasons. The first is that they are loud. Gamers tend to listen to very loud noises. Sure. Noise levels which you can barely hear your own thoughts. And in addition, those noises are with very broad spectrum. They are like a brick wall as in frequency domain, which means that it's a fair game. You cannot do any cheating. You have to find an algorithm which can remove them.
And so you've been working on multi-channel acoustic echo cancellation since 2007. And in hindsight, it's turned out to be very important for Microsoft. What drew you to this area?
Honestly, doing a multi-channel or stereo acoustic echo cancellation is a very difficult problem. Even the inventor of the acoustic echo cancellation from Bell Labs in 1998 wrote a paper stating that it is not possible to create a stereo acoustic echo cancellation. Since then, there was a lot of creative research in that area, and at the time it was quite challenging. So we we created a surround sound acoustic echo cancellation, which was demonstrated during Microsoft Research Tech Fest in 2008. And it was interesting coincidence that the 30 seconds movie clip we used was from the launch of Xbox. At that time, I had no information about the Kinect device and what is cooking in Xbox team, but noticed that during TechFest, a colleague of mine whom I know, it's a principal architect in Xbox team, started to bring more and more people. This is when I met for the first time Alex Kipman without even knowing that he is actually behind a new and very interesting and challenging device. A couple of months later, I finished my book, which was Nights and Weekends project, and decided that, okay, now it's time to return back to do more interesting and cool research. And then Alex Kipman came and literally drafted me to provide a set of technologies, the multi-channel acoustic echo cancellation, the microphone array processing for a new device, which at that time was called Project Natal.
Yeah. And so this also ended up in the product Roundtable. Was that before Kinect?
Roundtable was my first project in Microsoft research. At that time, it was called Ringcam. This is when I started to work for the first time on beamforming technologies, on sound source localization technologies, and I gathered a very interesting experience actually, starting from doing research and ending with finalizing a product. And that helped a lot for the technology transfers I did later.
Yeah. And so on the original Kinect, how long did you work on that project? Was it a multi-year project?
So for Kinect, I started to work around August 2008, and we shipped it in November 2010. So it looks like around 2 years and 2 months. And during that time, I had the challenging task to convert a working research algorithms into algorithms that can and code that can work in an industrial environment, in a device which is going to be released in millions.
And then you also worked on the new Kinect for Xbox One. What did you learn from the first Xbox that you took on to the Xbox One project?
So we thought that the microphone array and the audio design for Xbox One is going to be relatively easier because we already gathered a lot of experience working on Kinect device. The practice always proves us wrong when you believe that the next step will be easier.
Yeah.
So it happened that the microphone array in Xbox One is way more challenging acoustically. The microphone array is out of the device, it's separated, and the depth camera itself has enormous acoustical influence. The depth camera in the Xbox One is a little bit bigger, so we have 2 cooling fans near my precious super sensitive microphones.
Yeah.
And this is what basically justified taking the microphone array out of the device. So it's a separate block. When you see the microphone array, the Kinect in Xbox One, you see the 2 distinct blocks, the microphone array and the device and the depth camera. But the depth camera is sufficiently big to do some sound reflections, and this caused a lot of problems fixing here or there and making the microphones to capture the sound properly. And of course, we have a lot of improvements in the algorithms which process the signals from those 4 microphones and provide a better quality sound, which means enable the dashboard and the gaming designers to do more interesting scenarios, more challenging games, more interesting speech recognition capabilities.
So Xbox has a reputation for delivering lean, efficient computations for its system, leaving all the power to the game developers. What does that challenge look like for you?
So I still believe the Xbox team was and is one of the best engineering teams we have in Microsoft. The problem I have to face is that those are enormously highly trained software engineers. All the procedures for creating, debugging, and building the code, establish it and follow it strictly. But not one of them had, for Xbox Kinect, experience doing audio signal processing code, which means that they have difficulties to find the problem when it is not a coding problem, when it is algorithmic problem. And this is what basically forced me to go and to spend the 4 months before Xbox Kinect release there. I had office, I had desk there, I was working hand by hand and shoulder by shoulder with the software engineers. And what we tried to do for the Xbox One is to bring people with the proper qualifications. So now the audio team in Xbox consists of 4 people with PhDs in signal processing. So at least for me, it's way easier to work on new algorithms and to hand over the MATLAB scripts, and they can convert and debug and solve most of the problems which are specific for this particular implementation.
So in addition to shipping products and your research, you've done 70 research papers, multiple books, and you're listed on 40 patents. What does your day look like that you've got your time split between research, shipping products, and doing academic things like research papers and books?
How to say? Xbox Kinect converted my nice and cool research office into one of the focal points of a multi-billion-dollar business.
Yeah.
And this means a lot of people want to came over and to talk and to discuss the problems with their new projects, with their new products, and especially with the trend of converting Microsoft from software initially, then software and services, and now devices and services program. The demand for audio processing algorithms, for sound capturing algorithms, for good systems increased, because in most of the cases those devices are small. They don't have keyboard, they don't have mouse. So speech and speech recognition is one of the most convenient modalities, which means good microphones and good speech enhancement. Mm-hmm. So most of my day goes emails and meetings. So the 2 or 3 hours at the end of the workday is my time when I can do some creative work.
Yeah. You left academia for Microsoft Research years ago. Any regrets with that?
You know, I never regretted that, because it's one thing to teach your students on how to do engineering, and it's completely different to have impact, real impact on how people live, enjoy their time, entertain themselves, play games. And from this standpoint, Microsoft gave me the opportunity to make that impact. And unlike my years as a professor in the technical university, when I know I was a good professor, I prepared a lot of good engineers, but you cannot measure the impact. Now I know exactly how many people are using my algorithms in Xbox Kinect, for example.
Mm-hmm. So it's not very often that I get to spend some time in a room that's been calibrated. Tell us a little bit about this room and what you use it for.
So this room is, the technical term is anechoic chamber, mm-hmm. which means that there are 2 things happen here. First, looking at those edges, this means the sound does not reflect. It just gets absorbed, so we don't have reverberations. The sound you hear is just the direct path from my mouth to your ears or to the microphone of the camera. And the second is that it's a quiet place. When you close the door, this is a concrete cube which does not touch the building anywhere else than the floor, and we sit on this thick layer of rubber. Mm-hmm. So we don't pick the vibrations from the building and from the street. And when you are in a quiet and non-reverberant place, this is not a typical sensation for the human brain. So first, we are kind of used to hear reverberation, especially the one which is the reflection from the ground. This is a cue for distance for us. Mm-hmm. And actually, when you came closer, at some point, the human ears and brain will start to sense this as 2 different sounds. And this is when the alarm bell triggers, because this means the sound source is already closer than a critical distance, and it's either your dinner or you're the dinner of that day.
Yeah, yeah.
And the second is so from this standpoint, we're kind of hanging in the air. Mm-hmm. Somewhere very high, and we're not birds. Humans are not 3-dimensional creatures. They're 2.5-dimensional creatures. The second is silence. And our brain is used to get information from the external world, from sensors, from ears, from eyes, from all of our senses, and suddenly one of them does not give anything. So it starts to increase the attention towards that sense, and after a couple of minutes you start to hear in your ears. That's the blood in your vessels. After 2-3 minutes, you start to hear your heartbeat and the sounds from your body, how you're breathing, and you start to hear more and more of those.
So on Reddit, people say after like 45 minutes in anechoic chamber, you go crazy. Anything to that?
Not exactly crazy, but you start to have so-called acoustical hallucinations because the brain is a pattern matching machine.
Sure.
And the noise contains everything. So at some point it will be matched to something you have heard, and the brain will classify this, and nothing more than that. It's not that scary, but it's not a pleasant actually sensation.
And what's the longest that you've spent in here?
I have spent hours here, but pretty much doing something. There are always sounds of the equipment, instrumentarium, the loudspeakers. So I never basically spent, let's say, 1 hour on purpose laying on the floor in complete silence.
We'll try that next.
We can.
And so you've got a Kinect set up here with a kind of a weird U-shaped apparatus around it. What is this used for?
So stepping aside from this information deprivation, etc., this anechoic chamber is an acoustical measuring device. What we have here is an arc with a radius of 1 meter with 16 loudspeakers on it. And actually you can see that there are also 16 microphones. So this device can be used for measuring directivity patterns of microphones and radiation patterns of loudspeakers. So in this particular case, we have a microphone array, a Kinect device, in the center of this semicircle, so the motors can basically move the arc, and at each position you play certain sounds from the loudspeakers and record them with the microphones. And after 400 measurements, which takes around 6 minutes, we can actually draw the directivity pattern of the microphones of the Kinect device in 3 dimensions, and then use those to make our beamformers to perform better and to suppress the unwanted sounds better. And in the same way you can put, and it has been done actually, the Microsoft Surface device, and to measure the directivity patterns of the loudspeakers and to see how we can direct the sound more towards the human, which means less power, and to save some battery life, etc., etc. So it's an acoustical measurement tool, nothing more than that.
Yeah. What will customers experience with the new acoustic work in Xbox One?
With increase in developing this whole story and transforming Xbox, the challenges in front of the sound capturing and speech recognition and the speech-enabled dialogue system raise it enormously. It's one thing to recognize Xbox Play, Xbox Stop, etc., means a small set of commands, and it's completely different to use speech recognition to select one of 50,000 games, one of 300,000 songs, or one of 100,000 movies. And this requires way higher quality of the capturing of the captured sound, so we can allow the speech recognizer to do its own job.
So the sound isolation also, it helps with phone calls and making sure you hear people well, but it also works for the computer to isolate and better understand what you're saying.
That's correct. Communication scenario is one of them, but way more challenges for us now poses having a speech recognizer to recognize a large amount of words and to provide the proper input to the user.
And what's your next challenge at Microsoft?
I mentioned that the transition from software and services to devices and services company poses a lot of new challenges. There are a lot of new projects going on. Always there is some microphone or loudspeaker engaged. And of course, what we want to bring is to make the user interfaces of our computers to be more human-like, more native, more intuitive. And this means understanding better humans. Who is talking? What is the emotional state? How many people are they? When they talk to each other, when they talk to the machine, can the computer interject in the conversation with something meaningful and useful for the company, for the party, etc., etc. All of those questions, one way or another, they go through the microphones and loudspeakers, because the most native way we communicate between each other is actually human speech.
Great. Well, thank you so much for having us over today.
You're very welcome.